Today we're going to talk about the Bohr model of the atom. So the Bohr model really was the answer to the problems that nagged the Rutherford model of the atom. Remember the Rutherford model? We picture a central nucleus, got all the protons and neutrons located in this nucleus, and then firing around the outside like planets around the sun, you have these like electrons moving around these orbits. And a lot of people refer to this as like a planetary model because really most of the mass, like in our solar system, is located in the middle. And then you have these little things like planets circling around the outside. Now, we'd be living with the Rutherford model to this day if there wasn't any problems with it. And there was really two problems with the Rutherford model. The first one you've probably thought of yourself, and that is, hey, if all these electrons are going around in circles, that circular motion equals accelerated motion, centripetal acceleration. And I think we heard somewhere along the line that whenever you have an accelerating charge, you should emit electromagnetic radiation. So the fact that this doesn't happen as these electrons, which are definitely charged particles, go around this nucleus, they are accelerated and they don't give off electromagnetic radiation. That was a bit of a problem with the Rutherford model. Secondary to this, the second problem is, well, it's something we'll dive into with a little bit of detail, and that is the whole idea of what we call emission or absorption spectrum. And that's probably the focus of today's lesson. This problem that we'll talk about, and the Bohr model was very elegant at explaining. So first, a little background. I have a picture here. People found out quite a while ago that if you took different elements, you'll notice here we have helium, neon, argon, krypton, xenon. If you take these elements and put them in a vaporized form, if they're gases, great, they're already in their vaporous form. If you put them into an evacuated chamber that was made of glass, so that's what we see here, and then you put high voltage across them. So you can see up here, there's like an electrode, and we might make this one really positive, and there's an electrode down here, and we'll make this one really negative. When you apply this high voltage across this low pressure gas, it emits a characteristic light. So helium always glows this kind of a color. Neon, probably the most famous of these, what we call discharge tube, the neon light, gives off this orange glow. Argon gives off this, and this was, first of all, fascinating. Even though people couldn't explain it at first, it was fascinating to chemists because it meant that chemists could take a look at these different colors and start to identify certain gases just based on the color that they gave off. But if you really want to understand emission spectrum, or the light that's giving off by these gas discharge tubes, you need to take a look a little closer. And to look closer, you would take this gas discharge tube here and you would pass it through some narrow slits to make sure you just had a fine beam of light that came through here. And then you would take that fine beam of light and pass it through a prism. The alternative to this, we'll see, we can talk about this later. At any rate, you just want to break this apart into its different colors, and that's one thing that a prism does. And so you pass this light through a prism and you find out that each of those different elements will have kind of this spectral fingerprint. This light that we're looking at here happens to have lights in the wavelength of 410 nanometers, a violet band, a blue band, a blue-green band, and a red band. Now, when you put them all together, you'll get a certain color here. It might look mostly reddish, but when you break it apart, you see that that red is really made up of these four distinct colors. This is the hydrogen spectrum, by the way. It's really made up of these four colors. Put them together and you see the color that hydrogen appears to the naked eye. So emission spectrum at its basic is really this idea that when you take certain elemental gases, excite them by putting a voltage across them, they give off a light that when broken apart has certain characteristic bright bands. So we would call this an emission spectrum for hydrogen. So here's some other examples of emission spectrum when you break the light given off by certain gases under those conditions, and you break it into using a prism or a diffraction grating would work as well. You break it into its different parts. You see that sodium gives off these distinct colors. Hydrogen is the one that's most famous, gives off this red. All these different colors is violet down here. Calcium's a little more complicated. Mercury's here. But they're all giving off certain colors from the spectrum we're most familiar with, and that's the visible light spectrum, or this continuous spectrum that you would get if you did this experiment with white light. So if we go back to this, if this happened to be not hydrogen, but maybe, well, maybe instead of having this whole business here, we replace it with like a filament light bulb or light from the sun or something like that. And this light comes out and goes through these slits, we would expect to see the whole rainbow over here. So instead of just seeing these four certain bands, we'd get the whole continuous spectrum. So when we talk about the continuous spectrum, that's the kind of spectrum that's a rainbow, right? That's what you get from white light going through this spectrum. But these are emission spectrum. They are certain distinct bands. So let's get back to the Bohr model, or the Rutherford/Bohr model. Rutherford couldn't explain these bands. So it took Niels Bohr's new model to come up with a theory as to how these bands are being produced. All right, so we're going to talk, and we'll use the terms continuous spectrum to refer to this full spectrum Roy G. Biv. Emission spectrum, you'll see, are these bright bands we've already talked about. And then when we're done, I want you to challenge yourself to think about absorption spectrum a little bit, and how those could be explained using the Bohr model, just using a little bit of reverse thinking. So let's talk about the Bohr explanation of the emission spectrum. So the first thing Bohr did in terms of changing, and it wasn't a radical change, but he changed our idea about the atom, not by totally throwing out the Rutherford model, but he did say that instead of electrons going kind of anywhere around the nucleus, they had to be in certain distinct energy levels, right? So they could be in the first energy level. For example, we could find a electron here, and Bohr still thought of the electron as going around this nucleus, and it could be in the first energy level. And from your studies in chemistry, you know that when things are in their ground state, you can have as many as 2 electrons in the first energy level. Then you'll start filling up the second energy level, etc. And so we have Bohr to thank for this idea of these energy levels, these places where electrons can exist. They can be in this energy level or this one, but they can't be in between. So here's what Bohr suggested. He said, when you take a gas like hydrogen and you put it in this chamber, and you put voltage across it, you could imagine that the electron that's normally down here gains some energy and jumps to a higher energy level. So when you applied that voltage, you gave energy to this electron and it jumped up here. Now, this electron is in the second energy level, and it's not totally comfortable there, and it won't stay there real long before finally it jumps back down. Now, to make this jump up, we had to add energy. We added energy by using that voltage so that the electron could jump up to this higher energy level. Well, when it bounces down or jumps down, it has to lose energy. And the loss of energy that occurs is given off in the form of a photon of light. And so Niels Bohr said when atoms absorb energy, the electrons may jump from lower to higher state. That's step 1 right here. And then these excited electrons are not stable. They'll drop, step 2 here, to a lower energy state. And at that point, a photon is emitted that corresponds to the energy change of the electron. So whatever this jump is, whatever this drop in energy was, that's the particular photon that's given off by this atom, or this electron that drops down in this atom. Now, this is not an old idea. This is all about the law of conservation of energy. The electron can't jump up without gaining some energy or getting energy from somewhere. And when it jumps down, it has to account for that missing energy. As it loses energy, it has to give up that energy in some form. And in this case, it's the energy of this photon. And remember, the energy of a photon is h times f. So if you're giving off a particular amount of energy, then you're giving off a particular frequency of light. So if we go back to this idea of these different spectrum given off by these different um, gases, each one of these corresponds to some transition from a higher energy level to a lower energy level in these different atoms. So it's not unusual that every atom has different energies that are given off when electrons jump from a high state to a low state. And so every atom has a distinct emission spectrum. Now, we'll focus our attention on the simplest of all elements, and that is hydrogen. It's the most studied spectrum, and it's the simplest one to understand. And so here, instead of looking at this as like energy levels as these circles, let's look at the energy levels in terms of just how much energy they have down here in what we'll call the ground state. Oh, I should have changed this. I'm not a fan. So, oh, I understand why this is like this. Okay, this is the second energy level. It is actually. I thought it was the first, but go back to this. Here's the second energy level in hydrogen. And so if energy is absorbed by an electron, imagine an electron starts in the second energy level. If you give that electron some energy and it jumps up, it might jump up to the third energy level. And then when it jumps down, it emits this red light. Now, if that electron jumped up to the fourth energy level and then jumped back down to the second, that transition right there corresponds to energy equal to green frequency of light. And so you can see the emission spectrum for hydrogen is all because of transitions from a higher energy, either 6 to 2 or 5 to 2 or 4 to 2 or 3 to 2. And because the jumps are different, so you can think of this as a certain energy level and we went down a certain amount, the lowest jump will correspond to the lowest frequency, red. The highest jump will be the highest frequency, that's violet. Now, you might be saying, well, wait a second, all of these are ending in the second one. What about if it jumped down to the first energy level? Well, imagine if we made a transition all the way from, say, n equal to 6 down to n equal 1. You would say, well, shouldn't there be another photon of light? Because we got this red, green, blue, violet. And you're right, you would get another photon given off, except this photon would be in the ultraviolet. And so we wouldn't see that photon with our eye. We'd have to go looking for it with some sort of ultraviolet detector. And the same with any of these transitions. If you transition down to the first energy level, even the smallest transition from here to here, even though I don't have it to scale, this energy here still corresponds to ultraviolet radiation. And so the visible light spectrum for hydrogen is only the things that happen from a higher energy level down to the second energy level. Now, we should deal with something right now. There's probably some people scratching their heads saying, wait a second, hydrogen, I thought hydrogen only had one energy level, because that's what we learned in chemistry. So what's going on here? You're saying that there's 2, 3, 4, 5, 6. How many energy levels does hydrogen have? Well, the answer is as many as you want to consider. We could actually go beyond the 6th and say, well, what about the 7th? Now you'll notice something, that these are getting closer together. So the 7th would be closer to the 6th than the 6 was to 5. And 8 would be closer to 7. And you'll notice that if that happens, these things start getting really super tight on top of each other. So at some point, it's kind of unnecessary to think of anything beyond the 6th or 7th energy level, because the 7th and 8th and 9th are really so close together, they're essentially the same. So the answer to the question, how many energy levels does hydrogen have? You could say, well, it's got an infinite number. Does that look like an infinite symbol? Let's try that again. Yeah, that one's way better. You could say it has infinite energy levels if you really want to get ridiculous about it. But for all intents and purposes, once you get past the seventh and eighth one, you're really talking about energy levels that are right on top of each other. I like to talk about these energy levels. Sometimes I'll talk about these like stairs in a staircase. So you can start with the ground level, and then the first step is always the biggest one. So this, if I use hydrogen as an example, and I show the n equal 1, then this might be the second energy level. So that's step number 1. Then the third energy level might be right here. That's the n equal 3. So I like to think of these as this weird and wacky staircase in which the steps are not evenly spaced. But if a ball drops from here down to here, it loses energy. So if that happens to be an electron, if we think of this analogy as an electron, as it loses energy, it has to show up somewhere else. But in the case of a ball, it might be kinetic. In the case of an electron, it's a photon that comes off this thing with a certain frequency because of the energy. So if you really want to understand the emission spectrum of everything, including the invisible parts of the hydrogen spectrum, then you look at all these different series. They've been well studied. We're not going to look at them too much, but they all got names because they're so significant. So anything that goes from a high energy level ends in the first energy is called the Lyman series, and it's all ultraviolet photons that are given off. Here's the Balmer series. That's the one that's most interesting because it's the one that's the visible light. So they've colored it. So then you have anything from higher energies to the third. That would be the Passion series. Those are little drops. So now we're getting infrared radiation being given off. So you can see that there's actually more than meets the eye literally. If you look at the hydrogen spectrum, you'll see these four. But if you go looking in the invisible parts of the spectrum, you'll see even more than that. Okay, so let's wrap things up a little bit. Rutherford's model was great at doing what it did, but could not explain a couple phenomenons. Biggest one we're talking about right now is this emission spectrum. So Bohr made some improvements. He said, like, let's not think of these things as planets going around the sun where the planets could be at any radius. He said, let's think of the electrons having certain allowable radiuses, or what we'll call energy levels, and they're only allowed to be in 1 or 2 or 3, but they can't be in the 1.5 energy level. That's forbidden. This is starting to sound a little bit like quantum physics. Quantum meaning you can have a certain discrete allowable amount of energy, but you can't go in between. And this ties in really nicely with what was going on with the quantum world at the time. So Bohr said, I know what's going on with the emission spectrum. He said, electrons are starting where they're comfortable in the ground state, but by giving them energy, and I should mention, we can give them energy in lots of different ways. So be on your toes. It doesn't have to be electricity that gives them energy. If we in any way can give energy to this electron, it can jump to a higher energy level. Let's say, for example, it took, I don't know, I'll pick a random number somewhat, 2.8 electron volts to jump from here to here. That electron will exist up there for a moment. It'll rotate around here, but when that electron sees fit to jump down to the lower energy level, then the law of conservation of energy says that a photon is going to come off, and the photon will head off at the speed of light with an energy exactly equal to that 2.8 electron volts. Law of conservation of energy. Energy in equals energy out. We gave it 2.8 electron volts of energy to have it jump up here, so it loses 2.8 when it jumps down here. Now, keep in mind, there's a lot of possibilities here now. If we start with the electron here, nobody says we can't excite it maybe right away to the third energy level. What if we give it enough energy to get up there? Well, now the outcome could be a little different. We could have that electron drop in 2 steps, giving off 2 different photons here, one with a certain amount of energy, another one with a certain amount of energy. As long as these 2 energies add up to be the energy that we put in here, then everything works out. So we could have one big jump up and then 2 little jumps down. We could have one big jump up and one big jump down. There's all kinds of combinations that are possible here. So be aware of that. But in essence, Bohr just used the law of conservation of energy to account for this emission spectrum. Before we go though, let's talk about the absorption spectrum because we're indirectly talking about it all the time because the absorption spectrum is really the reverse effect. Imagine that we start with an electron in its ground state and we shine white light at that thing. Now, I don't have any white light, but let's use orange to represent. Pretend this is white light. So we shine white light at this atom. Now, white light has every color under the rainbow. So it's got red there, got orange, got yellow, got green. I am going to go through all these, so be patient. Red, orange, yellow, green, blue, indigo. What the heck is indigo anyway? I don't know, something like this maybe. And then violet. Well, that's practically violet anyway. Let's go here. Okay, so we got all these wavelengths coming through, and they're all going to have the possible interaction with this thing. But guess what? This electron is very picky. This electron can only absorb energies that are associated with jumping either one energy level. We could have it jump all the way to the second one. So because of that, when all these wavelengths come through, almost all of them end up on the other side. So when you go looking on the other side, you might still see the red. You might still see the orange. Yes, I'm doing this. But the yellow might be missing. And the green shows up. And the blue shows up. And everything in between all these things show up. But you might have a band of color in the, what did I say, the yellow spectrum that's missing. Well, guess what? That yellow energy was exactly the right amount for this thing to transition to a higher energy level. So where'd the yellow light go? Well, it got absorbed here and it's stored, the energy at least is stored now in this electron at a higher energy level. And then when it drops down, that photon can be emitted again, except you don't necessarily see it over here because the photon might head off in this direction. So if we go back and take a look at absorption spectrum, you'll notice that every one of the lines in the emission spectrum, all the lines that are emitted when an electron transitions from high to low, are exactly the ones that are absorbed in the absorption spectrum. So there's my violet, there's that one, there's this. So they're symmetrical, except this one is emitting those photons as electrons transition from high to low. This one is absorbing photons as the electrons jump to a higher energy state. So hopefully you hung in there and that makes some sense, this idea of the emission and absorption spectrum. And the biggest thing was Bohr's elegant explanation. It's fairly simple in its essence. Now, you're going to say, wait a second, did you forget about that other thing? The idea that as electrons orbit the nucleus, even if they are in certain energy levels, they're still going around and around. Are they still not accelerating? Shouldn't they be giving off parts of the electromagnetic spectrum? Shouldn't they be emitting radiation and losing energy themselves and eventually just spiraling into the middle of this thing? Well, Bohr didn't have an explanation really for that. All he said to try to keep people at bay and go with his model is he said, electrons don't behave that way. They can only absorb and emit radiation when they transition. When they are in their stable energy levels, they do not emit radiation. And he kind of just left it to somebody in the future to fully explain why. So we went with that, right? The Bohr model works really great as long as you suspend for a moment this problem of electrons that go around and around should be accelerating, giving off electromagnetic radiation. They don't. They only give it off when they transition up or down. If you can go with that, then you're good with Bohr. But let's face it, the Bohr model was somewhere approximately in the 1900s, like 1905-ish or something like that. This sucker is like 120 years old almost. So we're okay with a few missing pieces. I mean, heck, at the time Bohr came up with this, there was no cars, no phones, nothing going on. So to get this far with the model of the atom is great. And you're probably most familiar with this model of the atom is the model that got you through chemistry in high school. But I'm here to tell you, it's not the end of the road. It's the middle of the road. There's been improvements. We'll talk about them later in some vague details. But for now, Bohr model rocks.